Hello friends, good afternoon everyone. I am fine. How are you? I hope you will be fine. Welcome back in my channel, Dr.Satendra Kumar. Dear friends, if you want this type of videos relative to mathematics for higher education, then you need to subscribe, share and like my videos and my channel. Today we will discuss types of singularity. Okay? Now, singularity. What is singularity? A singularity of a function of a function fz is a point at which the function cj to be analytic. Okay? A singularity of a function fz is a point at which the function ceases to be analytic. Now, they are generally, singularity are two types, isolated and non-isolated. That is isolated and non-isolated. Singularity. Now define isolated and non-isolated. If z is equal to a is a singularity of fz, and if there is no other singularity, there is no other singularity within a small circle surrounding the point z is equal to a, then z is equal to a is said to be an isolated singularity. Isolated singularity of the function fz. Otherwise, it is called non-isolated. Now repeat, z is equal to a is a singularity of fz, and if there is no other singularity within a small circle surrounding the point z is equal to a, then z equal to a is said to be an isolated singularity of the function fz. Otherwise, it is called non-isolated singularity. Now explain with the help of an example. If fz equal z square plus 5 upon z z minus 3 z square plus 1 is analytic at every point, is analytic at every point except z equal to 0, 3, plus minus I. Hence, these are isolated singularities. Hence, these are isolated singularities. Okay? Of Fz. Now let us consider the function Fz equal 1 upon 10 pi by z. It is not analytic. It is not analytic. It is not analytic at the point where 10 pi by z is equal to 0. That is 10 pi by z is equal to 0 equal to 10 n pi implies z is equal to 1 upon n. N is equal to 1, 2, 3 up to dot. Please stop. Thus, z equal to 1, 1 upon 2, 1 upon 3 up to dot, z is equal to 0 are the singularities of the function, are the singularities of the function all of which are isolated, all of which are isolated except z is equal to 0, except z is equal to 0, because in the neighborhood of NBD of z is equal to 0, there are infinite number of other singularities, z is equal to 1 upon n, where n is large. Now we can say there are many points where function is suggested to be analytic. These functions are neighborhood of z is equal to 0. Therefore, at z is equal to 0, is a non-isolated singularity of the function. Now therefore z is equal to 0 is non-isolated singularity of the function. Okay. Now to explain the concept of singularity and poles, where these matter are defined singularity. Now we can say type of singularity. Now to explain type of singularity, let fz be analytic within a domain D except z is equal to A, which is an isolated singularity full stop. We draw a circle C with its center z is equal to A and radius as small as we wish, and another large concentric circle C, another large concentric circle C of any radius R capital R lying wholly within the domain D, lying wholly within the domain D. Now in the annulus between these two circles, fz is analytic. If z is any point of the annulus, then by Lorentz series fz equal summation n is equal to 0 to infinity an z minus a whole power n plus summation n is equal to 1 to infinity bn z minus a whole power minus n, where z minus a modulus greater than 0 less than capital R. Okay? The second term summation n is equal to 1 to infinity bn z minus a whole power minus n. On the right hand side is called the principal part of fz. Principal part of fz at the isolated singularity. At the isolated singularity z is equal to a. Full stop. Now there arise three possibilities. First possibility, all beyonds are 0, imply no term in PP principal part. This is the removable singularity. In this case, when all bn are 0, that is no terms in principal part, then at z is equal to a, function has removable singularity. In second possibility, infinite number of terms, in PP principal part, then at z is equal to a, function has essential singularity. Essential singularity. Okay? Now in third possibility, finite number of terms in principal part, that is PP, then at z is equal to a, function has whole. Okay? Now repeat. There are three possibilities at z is equal to a. Then if all bn are 0, therefore we can say there are no terms in principal part. Then at z is equal to a, function has removable singularity. In second possibility, infinite number of terms in principal part, then at z is equal to a function has essential singularity. Now in three possibilities, finite number of terms in principal part, then at z is equal to a function has pole only. Now explain detail. Number 1, removable singularity. Removable singularity. Here fz equal summation n is equal to 0 to infinity an z minus a whole power n, which is analytic for z minus a modulus lesser capital R, except z is equal to a. Let phi z be the sum function of the power series summation n is equal to 0 to infinity an z minus a whole power n. Now define sum function. Sum function is a function of any power series which represent the power series. Full stop. Phi z is a sum function of power series. Summation n is equal to 0 to infinity an z minus a whole power n. Now phi z differ singularity. We can suitably define fz at z is equal to a so that we have phi z equal to fz or a0. Now for z minus a greater than 0 less than capital R, for z equal to 0, example, let fz equal to sin z minus a upon z minus a has removable singularity at z is equal to a, has removable singularity at z is equal to a because sin z minus a upon z minus a, this is equal to 1 upon z minus a. Now z minus a minus z minus a whole cube upon factorial 3 plus z minus a whole power 5 upon factorial 5 minus up to dot, this is equal to 1 minus z minus a whole square upon factorial 3 plus z minus a whole power 4 upon factorial 5 minus up to dot. Okay? The function f z minus a upon z minus a has no term containing negative power of z minus a. However, this singularity can be removed and the function made analytic by defining sin z minus a upon z minus a equal to 1 at z is equal to a. Okay, now here z is equal to a. Sin z minus a upon z minus a has removable singularity because take sin z minus a upon z minus a, z minus 1 upon z minus a as it and the expansion of sin z minus a. Now in this case 1 minus z minus a whole square upon factorial 3 plus z minus a whole power 4 upon factorial 5 minus up to dot has no terms containing negative power of z minus a. However, this singularity can be removed and the function made analytic by defining this at z equal to a. Okay? Now, second possibility is or second is singularity, essential singularity. Essential here the series summation n is equal to 1 to infinity z minus a whole power minus n bn does not terminate. Now example fz equal to sin 1 upon z minus a has essential singularity at z is equal to a because sin 1 upon z minus a expand by formula 1 upon z minus a minus 1 upon factorial 3 z minus a whole cube plus 1 upon factorial 5 z minus a whole 5 minus up to dot has infinite number of terms has infinite number of terms in the negative power of z minus a. Okay, there are infinite number of terms in z minus a. Now this is an example of essential singularity. Now third condition, pole. Here the series summation n is equal to 0 to infinity, n is equal to 1 to infinity, bn z minus a whole power minus n consists of finite number of terms then at z is equal to a is said to be a pole of order m of the function f(z). When m is equal to 1, the pole is said to be simple. The pole is said to be simple. Okay? Now example. Fz equal sin z minus a upon z minus a whole power 4 has a pole at z is equal to a. Because sin z minus a upon z minus a whole power 4, this is equal to 1 upon z minus a whole power 4, and now extension z minus a minus z minus a whole cube upon factorial 3 plus z minus a whole power 5 upon factorial 5 minus up to dot. This is equal to 1 upon z minus a whole cube minus 1 upon factorial 3 z minus a whole 1 plus z minus a upon factorial 5 minus z minus a whole cube upon factorial 7 plus up to dot. Has the finite number of terms. Has the finite number of terms. Here first two terms only. First two terms only. Now 1 upon z minus a whole cube and minus 1 upon 3, 1 upon z minus a, there are two terms only. Okay? In a negative power of negative power of z minus a due to fz has a pole. Thus, if z is equal to a is a pole of order m of the function fz, then fz equal summation n is equal to 0 to infinity a n z minus a whole power n plus b1 upon z minus a plus b2 upon z minus a whole square plus up to dot bm upon z minus a whole power m. Now take common 1 upon z minus a whole power m. Now in bracket summation n is equal to 0 to infinity a n z minus a whole power n plus m. Okay, plus bm minus 1 z minus a plus up to dot b1 z minus a whole power m minus 1 bracket close. Now it can be written as 1 upon z minus a whole power m phi z. Okay, since phi z tending to bm as z tending to a, hence phi z is analytic. Phi z is analytic in the neighborhood of the pole z is equal to a. Okay, now question, find out the zero and discuss the nature of the singularity of function fz equal z minus 2 upon z square into sine 1 upon z minus 1. Answer, zeros of fz by fz is equal to 0, that is z minus 2 is equal to 0, comma sine 1 upon z minus 1 is equal to 0. Now z is equal to 2, comma 1 upon z minus 1 equal to n pi. Now pi is n is equal to 0, 1, comma 2 plus minus 1, comma plus minus 2 plus up to dot. Now z is equal to 2, comma 1 plus n pi, 1 upon n pi, where n is equal to 0 plus minus 1 plus minus 2 dot dot dot. Okay, this is the zeros of the function z is equal to 2 and 1 plus 1 upon n pi. Now n 0 plus minus 1 comma plus minus 2 up to dot dot. This is the 0 of the function. But at z is equal to 1 is an isolated singularity. Is an isolated singularity. Okay. Now poles of fz are given by z square is equal to 0, that is z is equal to 0, and z is equal to 0 is a pole of order 2. Z is equal to 0 is a pole of order 2. Okay, student?